Hey, we're back for lecture 5.6 on maximum and minimum values. This is where we do a lot of the Calc 1 techniques that we did, especially applications towards optimization for multivariable functions. So we're going to define the critical point of a function. That's our first goal. And this will be fairly similar to what we did in Calc 1, where the derivative vanished or the derivative was undefined. And in this case, we have multiple derivatives, the partial derivatives, and we'll package things together using the gradient function and talk about critical points. Next, the most important thing that we'll learn is how to test critical points and boundaries, which are our general version of the endpoints of intervals, to find local maxima and minima. These will be the maximum and minimum values of the functions compared to nearby points. And in order to find a global maximum or a global minimum, that means the largest or smallest value that the function can achieve on any values in its domain, will be a harder problem, but we'll also learn techniques that help with that as well. And finally, we're going to learn a version of the extreme value theorem, which talks about maximum and minimum values of a function on a closed interval in Calc 1. We'll learn a value of this for multivariable functions that now expand to talk about closed and bounded sets in the XY plane or in higher dimensions. So that's the goals for the video. Let's start talking about local extrema or extreme values of a function. So if you remember the term extremum or extreme value from Calc 1, it means the values of a function that are locally the largest or smallest among nearby points. And here's the official definition. If we have a multivariable function f of some number of input variables, here it's listed x1, x2 up to xn, we will say that a point in n-dimensional space is a local maximum of the function. And the point for this to make sense needs to be in the domain of the function. A point P is a local maximum if f of P, its output value, is larger than or equal to f of Q for all Q in some neighborhood around P. And I'll remind you of what that means in a moment. Likewise, a local minimum, or a P, that point is a local minimum if the output value f of P is less than or equal to f of Q for all Q in some neighborhood around P. And what we mean by neighborhood explicitly is draw a small circle or a small sphere or a small hypersphere. And in mathematical terms, that means the set of points of some fixed distance or smaller away from the center, and draw that set around P. So for us, when we're working in one dimension for single variable calculus, the single variable calculus version of drawing a small neighborhood around a point is to take an interval of values with center at that point. In two dimensions, which is what we'll be working with today, in the XY plane, we will draw circles around the point, and those are what we mean by a neighborhood. So for values nearby or within a certain distance of the point P, if f of P is the peak or the value of the graph of the function at that point, we'll call it a local maximum or local minimum, respectively. Now, here's the main question. You probably have some recollection from Calc 1 of how to identify possible points that are local max or min points. And this is using the first derivative or by identifying critical points. So in multivariable calculus, we have multiple directions to travel in our domain, or in other words, we have an x and a y direction to change our input variable and our input point P. And to basically explain why those two directions of derivatives are good enough, I want to start with the following observation. If we look at we'll start here at the top of the slide. If we look at the x directional derivatives, the partial of f with respect to x evaluated our point P. And if we're able to plug in P and get some non-zero number, remember that the partial derivative measures the rate of change of the function f, or the change in the output variable z with respect to just the change in x in this case. And if that number is non-zero, that means it has a positive or negative slope. And that means we can change the x variable input for P by a small amount and either increase or decrease the function. So in that case, if that derivative is non-zero, the point P cannot be a maximum or a minimum locally. Likewise, and this is a typo, this should say f sub y. So if the y directional derivative is non-zero at a point, then we could travel in the y direction by a small amount in either direction to either increase or decrease the value of the function. And if you flip things around, this means that if we know a point is a local maximum or minimum, then the x and y directional derivatives both have to be 0, as long as they're defined. If either one is undefined, we'd also want to investigate those points. And this is how we define the notion of a critical point in 2 or higher dimensions, or two or more variables that are input variables. Here's a picture denoting what we just explained, which is if the tangent lines, which are those slopes, the slopes of whom are the two directional derivatives that we just identified, if those tangent lines don't have slope 0, then we can increase or decrease the height of the function off of the xy plane by moving along those cross sections drawn in blue. So if the y directional derivative is not 0, this line is not parallel to the xy plane, then we can move up or down the blue curve and get higher and lower values. So it can't be a local max or a local min. And likewise, if the x directional slope is like this. So let's give this a name. And we can package things together with the gradient function, since the components of the gradient function are those two partial derivatives with respect to x and y. We will say that a point P with coordinates x and y is a critical point of f if one of the two following conditions happens. If the gradient of the function f vanishes at P, or if, in other words, if we plug in P to the gradient and we get 0, 0 for its two components, that means both partial derivatives vanish, then that's a critical point of the function. Or if one or both partial derivatives fail to exist, this would mean the gradient is not defined at P, and we'll also say that that's a critical point. You should think of a critical point that's defined this way, where the gradient is undefined, as a point to go investigate further. It's not necessarily a max or min of the function, but it could happen, just like we have the notion of a sharp corner or cusp in single variable calculus, that could be the max or min of a function. And here's a theorem. We're going to use this without any justification. That should feel familiar to what we learned in Calc 1, that the local maximum and minimum values of a function can only occur at critical points. So again, local max and min only occur at critical points. And the way that we use this in practice is if we want to find local max and min for a 2-variable or higher function, we go identify a list of critical points and cross our fingers that it's a list we can check explicitly to compute the values of. And then the theorem says the max and min values have to occur at one of those points. Let's do an example to practice. So here's a function written as the graph of a function f of xy shown there, and we set z equals f of xy to get the graph in 3 dimensions. And we're told that this function, or this graph, has a minimum value. Let's find that minimum value. So given the information that this has a minimum value, and in light of the previous slide, our strategy here should be to identify all possible critical points of this multivariable function. And that's what I'm going to start with. And we'll do this every time on similar problems. If you want to pause the video now and try to compute some of the things you see on this slide, then go ahead and do that. This is just review so far from our partial derivative section and the gradient recently. So if you're all set and you have your gradient calculated, I'm going to do it with you now. The components of the gradient function, again, are the two partial derivatives of f with respect to x and y. So let's compute the partial derivative with respect to x. This is going to be 4x plus 4, and the rest of the terms don't have x's, so they are constant and go to 0 when we take the derivative. The partial derivative with respect to y is 2y minus 6, and every other term those were these two terms, every other term is a constant with respect to y. So those are our two partial derivatives, and the gradient function is the vector with these two formulas and its components. So it's a function that's also a vector, or a vector value function, we call it. And we want to know, to identify critical points, where this expression, we'll put these two, I'll even write it here, into a single vector. We want to know where this is the 0 vector, or where both components are equal to 0. Or part 2 of the definition said where this is undefined, but since these are polynomial expressions, these are never undefined. We're only looking for zeros of these two functions. If you look closely, you'll see that the first component is 0 exactly when x equals -1. It's a linear function. You can solve for x pretty easily. And likewise, the second component function happens to be 0 when y is equal to 3. Again, it's a linear function. You can solve for y. This could be more complicated in future problems. But in any case, a critical point needs to have both of these components equal to 0, So the x component has to be -1, and simultaneously the y component has to be 3. So there's only one critical point on our list to go check. Well, we're told that we're told that the function has a minimum, and we only identified one critical point, so this actually has to be the minimum unless we were fed faulty information. In this case, let's go identify the actual minimum value of the function by plugging these coordinates into the function. So I'm going to plug -1, 3 into my expression for x at the top of the screen. I see I get, let's see, 2 times -1 squared. That's going to be 2 minus 4 plus 9 minus, let's see, 3 times 6 is 18 plus 13. And let's do, I'm going to work from right to left, because why not? That'd be -5 plus 9 is 4, minus 4 is 0, plus 2 is 2. So you should get a minimum value of 2. So whatever this function looks like, we're told it only has one minimum value. So every other f of xy value, if we're not at the point -1, 3, has to be larger than or equal to 2. But in fact, that's be larger than 2, because if there was a f equals 2 or z equals 2 point anywhere else, it would have been picked up by our calculation of the minimum. So great. We just identified we actually identified all possible critical points and all possible max and min values. We found that there's only one critical point and it's a minimum. So this function has to have points of any height that you want above 2. All right, let's see what else we can learn. Here's a graphical depiction of what's going on with critical points. We've actually seen this phenomenon before in a previous classwork activity, but I want to put things on a more rigorous footing so we can discuss maximizing and minimizing multivariable functions with a little more certainty. So let's suppose we've identified a critical point P. We found some point in the xy plane where both partial derivatives of our function are 0. A critical point could be a local maximum. And for that to be true, the curves that we draw through our point that lie on the surface, z equals f of xy, have to be sloping downward in all directions. So local maximum has to have curves that slope down and away from the point in terms of the height of the function. And I want you to start thinking about what this means in terms of higher derivatives of the function. Just like we have the concavity or second derivative test in Calc 1, we can use similar aspects of our multivariable function to identify max versus min. On the other side, before we put a little more words and formulas to this, we could have a critical point that's a local minimum. And what this would mean is that, well, it's the smallest value compared to nearby points. And in this case, the curves that we draw through our point that lie on the surface will have to curve upwards in all directions. This is an example in the picture of a local minimum at the origin. And there's actually one more thing that could happen. Because all of the directional derivatives, those will be the slopes through curves, to the slopes of lines to curves that pass through our point, are completely determined by the gradient, which is given by the two partial derivatives. There's really only one other situation that could occur, which is that in one direction, the curves slope downward, and in another direction, the curves slope upward. And in this situation, it doesn't necessarily have to slope the saddle. We'll call this a saddle point, as it states on the slide. The saddle doesn't necessarily have to be lined up along the x or the y axis, but because the x and y directions completely determine the behavior of all of the directional derivatives and therefore the slopes that we're looking at on this graph, there's only those three possibilities. All of the slopes point upward because they're all combinations of the x directional and y directional slope. All of the slopes point downward, or some of them point down and some of them point up, and it'll have to look like a saddle like this. And without going any deeper into this, I just want to give you the second derivative test that we could have come up with by studying a few example functions, but here's what we're going to use to classify critical points in many problems. So let's suppose we have a two-variable function f of xy, and it has to be differentiable at our point P, which means that the derivatives, all of the partial derivatives, and let's even throw in all of the second partial derivatives, will exist at P. And let's suppose that we've already identified this point as a critical point, which explicitly means that the two partial derivatives f sub x and f sub y are equal to 0 at that point. We want to classify whether or not this point is a maximum, a minimum, or a saddle point. Those are now the three options. And to do so, we're going to compute this quantity called d, which involves all three of the partial derivatives of our function. Notice that there are actually four partial, all of the second order partial derivatives of our function. Notice that I've only really written three of the four possible second order partial derivatives. There's the second order partial with respect to x twice. There's the partial with respect to y twice. And then there's the partial with respect to x and then y. And keep in mind that there's also a derivative f sub yx, but assuming that all of our functions, all of our derivatives exist and are even differentiable at our point P, fxy will be equal to fyx by our theorem of mixed partials. So capital D is sometimes called the discriminant of our point P. Notice that this is a number, not a function, because we're plugging the point P into each of the second order partial derivatives, taking these two products you see here, and then taking the difference of those quantities. And here's how the theorem, the second derivative test for multivariable functions goes. If this quantity D is positive, then you can take either of the second order partials with respect to a single variable, either fxx or fyy. And the theorem doesn't say this, but this will be the case. You can take either of those values and check if it's positive or negative. So if D is positive, this discriminant, then we can use exactly one of the second order partials with respect to only one variable to check if P is a local minimum or maximum. And if the second order partial, let's say fxx is positive, you should think of this as a concave up function at this point, then P is a local minimum, meaning its output value f of P is smaller than nearby points. If, on the other hand, the discriminant is positive, but the second order partial derivative fxx is negative, you should think of this as a concave down function at the point, then P is the local maximum of the function. And again, I want to reiterate, if for some reason it's easier to compute the second part of this statement using fyy, you're free to do so. The same conclusion holds, even though the slide doesn't say it. So if fyy is negative, that's a downward sloping function, a concave down shaped function, and we'll have a local maximum. On the other hand, D also detects saddle points, because if D is a negative value, then P turns out to always be a saddle point. And finally, if D is equal to 0, so if the product of these pure second order partials is equal to the square of the mixed order partial fxy, then the test gives no information. And we actually saw a similar thing in single variable calculus, where if the concavity is 0 at the point, we actually can't tell if the point is a maximum, minimum, or neither. So just to review, this is a direct generalization of the single variable calculus second derivative test, which told us that concave up at a critical point determines a minimum value, concave down at a critical point determines a maximum value, and no concavity is indeterminate. And that's about all you can say in single variable calculus land. Although the statement of the second derivative test for multivariable functions looks a little more complicated, it actually knows more information. It has more possible outcomes than the single variable calc version. And just to reiterate, if we compute this quantity D, which we're going to practice with, and check if it's positive, then there has to be a maximum minimum, and we just determine that by looking at the concavity in the x or the y direction. If, on the other hand, D is negative, then we automatically know the point is a saddle point, and therefore cannot be a maximum or a minimum. It's only inconclusive, the second derivative test, if we get a discriminant of 0. Just for a little extra behind the scenes magic, this quantity D, which I'm calling the discriminant, is secretly the determinant of a 2x2 matrix called the Hessian of F. So if you look closely at this expression, if you've seen the formula for the determinant of a 2x2 matrix, if I had A, B, C, and D, this would be AD minus BC. Then this matrix, this 2x2 matrix with the partial derivative, the second order partial derivatives of all different types lined up in the rows and columns of this matrix, this is called the Hessian of P. And the determinant of the Hessian helps determine what type of critical point that critical point is. And in particular, the positivity or negativity of this determinant helps you decide if there's a local max or min versus a saddle point at that point. If you prefer the determinant formula versus this discriminant formula that I gave you, all you have to know is you compute all 4 partial derivatives to the second order of your function and throw them into the matrix. And if you don't remember much about determinants of matrices, even 2x2 matrices, this is an okay slide to ignore. Here's a graph of a function, z equals cosine of 2x plus y plus xy. And by the graph of the function, it looks like there's a local maximum of the function at the origin at 0, 0, or in that neighborhood. If you wanted to determine this mathematically, you would want to compute, first of all, the gradient of this function, check that the 2 components of the gradient vanish or are equal to 0 at the point 0, 0, and then further use the second derivative test to classify the origin as a relative local maximum of the function. And again, this will mean that, let me go back 1 slide, or sorry, 2 slides. This will mean that the discriminant of the function is positive, and to get a local maximum, the concavity in the x or the y direction is negative, which means take the second order partial fxx or fyy, you'll see that the concavity is negative in either direction. We will do a few more examples together when we practice computing things related to extreme values or related to possible max or min, those critical points. But let's first state the multivariable version of the extreme value theorem, so we have all of our tools at our disposal. And before I read this out loud, I want you to think back to what the extreme value theorem said in Calculus 1. It said that if we had a continuous function on a closed interval, then that function achieved its maximum and minimum values somewhere on the interval. So that's the basic statement of the extreme value theorem, but in practice, we used something called the closed interval method in Calc 1 in order to identify and compute the maximum values of a function on a closed interval. And the way that we used that method, the closed interval method, is by identifying all of the critical points of the function on that interval, throwing those into a list together with the 2 endpoints of the interval, and then testing the output values of the function, or in other words, the heights of the function at that list of values. Things won't be quite so easy in 2 variables or more when we have x and y as our inputs, or more variables than that. And the reason is that we can have a more complicated boundary of our domain or boundary of our closed set than just the 2 endpoints of an interval. So here's the statement of the extreme value theorem, and we'll go unpack it in the next few slides. If we have a continuous function f, and this actually is stated to work in any dimension, but imagine that this is happening in the xy plane. So if we have a continuous function f on what's called a closed and bounded domain D, then f has a global maximum and a global minimum somewhere in D. We'll talk about closed and bounded in the definition below, but I just want to point out that the statement of this theorem has global instead of local max and min. And global means that among all possible values of the function on that domain D, these are the largest and the smallest possible values of f of xy, respectively. So let's talk about what it means for a domain, the domain of our function, to be closed and bounded. So for a set D in n-dimensional space, again, think of some set that we've drawn in the xy plane, to be closed, it means that it contains all of the points on its boundary. What this means in practice is if we have inequalities defining our region, then they are less than or equal to or greater than or equal to, or when we draw the picture, we have a solid line rather than a dashed line. We'll see some examples of this coming up in the video, but just to preview, if you ever have a strictly less than, or you drew a dotted line to draw your boundary in the xy plane, your region in the xy plane, that's the domain of a function, that will be what's called open or half open or something other than closed. So closed needs solid lines, and it includes the boundary points. Bounded, on the other hand, seems a little more complicated, but it's actually not too hard to think about once you see a few examples. A domain or a region in the xy plane is bounded if there's some upper limit to how far its points get away from the origin or any other point that's fixed in that set. It's a little complicated to state. I'm going to give you another way of thinking about this in a moment. But the opposite of being bounded is being unbounded, which means there are points of this region D that are arbitrarily far away from the origin, or in other words, are as far away from the origin as you can possibly think. And if you keep moving farther away from the origin in every direction, you'll eventually encounter more points of this set D. That's what it means to be unbounded. So what does it mean to be bounded? The simple way to say this, just like we rephrased the definition of neighborhood to say draw a small circle or sphere about the point, for bounded means that you can draw a circle of some radius around the entire set D and enclose all of the points of D. And if you cannot draw a single circle of a single finite radius around the set, that means it's unbounded. If, for example, you try to draw a circle and some of the points of D lie outside that circle, and you keep expanding the radius of the circle to capture more and more points, but you're never able to capture all of D within a circle, then it's an unbounded set. On the other hand, if you can choose some large enough circle to capture everything, it's called a bounded set. By the way, the same terminology works for one variable, where you can imagine the x-axis in the xy plane just as our real number line, which is an input for the function, and then the heights can be mapped onto the y-axis or the y direction. And you can imagine still drawing circles about points. Let's say if we drew a circle about the origin, then we could capture some number of points, some really circles worth of points in the xy plane. And if we just look at their x components, then these will give us things like closed and bounded intervals on the x-axis. So for one variable functions, the extreme value theorem just requires that the domain of the function just on the x-axis be some collection of finite closed intervals. And maybe we can even have points by themselves. I could have shaded in the point at 1/2. That's okay as well. Closed means that we include all endpoints of intervals in single variable land, and bounded means that I can draw some interval around all of the points, and that interval has finite length. Okay, what happens in two variables? Let's look at some examples. So in some sense, because of the definition of bounded, meaning at most a finite distance away from the origin, the simplest type of closed and bounded domain is a circle where we shade the inside of the circle and include the boundary points. For example, all of the points on the boundary of and inside the circle of radius 3 centered at the origin constitute a closed and bounded set D. And algebraically, we can write this set down by saying the points x comma y in this set have to satisfy the inequality x squared plus y squared is less than or equal to 9. Oh, sorry. The way to think about this equation visually, if I hadn't given you the graph to start with, is these are all of the points x comma y whose distance, which is the square root of this number, is at most 3 from the origin, or whose distance squared is at most 9. So these are all the points at most distance 3. If I drew a line of length 3 from the origin out to this point and then just rotate it around, you'd get the whole circle. And at most means we can have things at a smaller distance from the origin. On the other hand, if we failed to account for those boundary points, if we drew a dashed circle but still included the interior, this would correspond to the strict inequality where the distance squared is strictly less than 9, or these points are strictly smaller than 3 units away from the origin. This is not a closed set, even though it's still bounded. So it's not closed because we missed some boundary points. To discuss the difference between bounded and unbounded, well, actually, here's 2 more examples of not closed sets before we talk about boundedness. If we draw a rectangle and have dotted lines on any of the 4 sides, for example, here we don't include the top and bottom of the rectangle, this would be a not closed set. I'll give my dogs a chance to bark it out for a sec. And I want you to think about both these examples as examples of not closed sets while I see what I can do over here. She just wanted to join the party. This is, I think I've introduced her before. This is Begonia. So the figure on the left is not closed because we didn't include 2 of the sides of this rectangle. Another way for a region to not be closed is for any of the interior points to not be included in the set. So the definition was a little rough and ready. We said we need all of the points on the boundary to be included. But actually, if we miss anything on the interior, we will also call that not a closed set. And the reason is, as soon as we poke a hole in our rectangle, this point becomes part of the boundary. We haven't given a rigorous definition of the boundary, but you can imagine if we widen that circle a little bit to not just include one point, but a small collection of points, then even though they're on the interior of this rectangle, you can think of that as a boundary of the object. It's a region where if you cross through that dashed line or that dashed curve, you exit the shape, even though you're exiting into this small circle on the interior. And any place where you exit the shape, if you cross that line or curve, will be considered the boundary. And in this case, you cannot cross through that point without leaving the set, and the point's not included. So if you don't like that definition and that example didn't make much sense, you can think of this algebraically, that even though we have inclusive inequalities, we have less than or equal to everywhere for the outside of the rectangle, we're still missing a point. So anytime you have a not equal sign for some point, you should be skeptical and try to draw the picture and see if it's closed and bounded or not. By the way, all of the examples that we've seen so far have been bounded, because if I draw a large enough circle around any of these four sets on these last two slides, you can enclose all of the points within that circle. To see an example that's unbounded, let's go back to our rectangle and fill in those dashed sides. This is now a closed and a bounded shape. It's closed because well, you can see in the picture, I shaded inside of a rectangle and drew a solid line to bound it. In terms of inequalities, I have inclusive inequalities in this definition of the region. And it's bounded because if I drew a circle, you can just imagine with me, here's the circle, I can enclose this thing. And if you wanted the smallest possible circle, I could just figure out the distance to the corners of this rectangle. And then I'd have a circle of that radius capturing the entire rectangle. If I only specify some conditions on the x coordinates, let's say that the x coordinates of my region have to be between -2 and 2 inclusively. This is like extending the closed interval from -2 to 2 vertically in both directions forever. This is an unbounded shape because no matter what circle I draw, there will always be points of height greater than the radius of that circle, or less than the, in the downward direction, same thing. And we can't capture those points with any circle of finite radius. So this is an unbounded figure. These are basically all the possible types of domains that we'll see in this class, but you can get a lot crazier than this and talk about closed and bounded in really sophisticated ways. So let's talk about how to find a global maximum of a function. And if you want to minimize this function, I'll leave that for you to do separately. We're going to do all the steps of this together. And I'm sorry that the figures got cut off on the slide below. I'll show these once we flip over the tablet. So in this problem, we're going to look at the function f of xy given by x squared plus 2y squared minus x squared y. And we're going to look at this function on a restricted domain. So this, of course, is defined on the entire xy plane because this is a polynomial. But if we just look at this on the following set defined by the algebraic conditions that x squared plus y squared is less than or equal to 16, and x is less than or equal to 0, this will define a region in the xy plane that we'll consider to be the domain of this function f. We're going to ask if f has a maximum value, and how do we know? And once we've assessed that question, we'll try to find the critical points of f, check if they have to be the maximum or minimum, and we're just going to do the maximum together, and then ultimately put things together using the second derivative test and the extreme value theorem to identify and compute the maximum value of f on this domain D. All right. Are we ready for it? Let's do it. So by the way, here's what the two pictures that got cut off look like. First of all, the domain itself looks like x squared plus y squared less than or equal to 16 says points of distance at most 4 away from the origin. So that would be the entire circle. But if we also specify that x coordinate is less than or equal to 0, then I'm just taking the semicircle in the second and third quadrants shown here. You'll notice that, and actually we'll get to this in a moment, but you'll notice that this is an example of a closed and bounded region. We'll talk about it in a little more detail, but first of all, is f a continuous function? We want to say, yes, f has a maximum value because f satisfies the conditions of the extreme value theorem for multivariable functions. So is f a continuous function? Well, as I already said, this is a polynomial in x and y. So yes, it's a continuous function. Is the domain closed? Well, the domain is drawn here, this semicircle in the left half of the XY plane. And if you check the conditions, they're inclusive inequalities. Or if you check the drawing, I've shaded or I've drawn solid lines and curves to bound this region. So yes, this is a closed region. All of the boundary points are included in the picture. And finally, is this bounded? Well, yeah, I could actually just extend the circle and here's a neighborhood of the origin that includes all of the points. But if you really wanted to be, sort of dramatic about it, you could take an even larger circle and you can really put the circle wherever you want. But all of these points will be, all of the points in the blue shaded figure will be within the confines of the circle. So it's a bounded region. And you do that algebraically by picking some conditions that these satisfy. Say that all the points are at most some distance from the origin. And in fact, they're all a distance at most 4 from the origin, because that's exactly what this inequality tells you. So what does that tell us? Well, we have the extreme value theorem for multivariable functions, which says that if f satisfies these 3 conditions, then f has a global maximum somewhere on the domain D. And now we just have to find it. So let's do part B of this problem, which is let's identify the critical points. These are points where the partial derivatives with respect to x and y both vanish. We'll identify those in a moment. And they are places where f could have a local max or a local min. In this case, we'll be interested in local max. And if so, we'll want to compare it to the other possible places where f could have a maximum, which will be on the boundary. That will require a little bit of work. Let's start by finding the critical points and assembling our list of points to test. And first of all, let's compute the 2 partial derivatives. Here I see the x derivative is 2x minus 2xy. And the y derivative is 4y minus x squared. And we want to know where this pair of functions is equal to 0, where the gradient is equal to 0. And you'll notice if I set the x partial derivative equal to 0, that this reads, I'm actually going to factor out a 2x to make my life a little easier. Set this equal to 0. This reads 2x times 1 minus y equals 0. And for that expression to be 0, either of the 2 factors in the product have to be 0. So either x is 0 or y equals 1. Those are the 2 solutions to this being 0. On the other hand, let's save that information. So any point that is a critical point of the function has to have its x coordinate equal to 0, or if it doesn't, it has to have the y coordinate equal to 1. Those are strict requirements on our set of critical points. That already identifies a smaller set than the whole xy plane. But let's cut things down further and see if we can get a finite list by looking at the y directional derivative, which is 4y minus x squared. If we set that equal to 0, this can be rewritten as x squared equals 4 times y. So we know that these 2 conditions have to hold. And by applying those conditions to this second piece of information, namely this other equation we've determined, we can try to find a finite list of points satisfying all of the criteria together. So if the x coordinate is 0, looking at the second equation, x squared equals 4y, that means that, well, x squared then is 0, so y has to be 0 as well. So in that case, we get the point 0, 0. The origin is a critical point of this function. On the other hand, if y equals 1, and by the way, let's just think about it. If x is equal to 0, we can even go back to the this is fy, right? If x is 0, the only way, so this is all gone, the only way for the remaining partial derivative to be equal to 0 is if y is also equal to 0. So the only possible critical point that has x coordinate equals 0 is where the y coordinate also equals 0. On the other hand, if y equals 1, then we get the expression x squared equals 4, which has 2 solutions, x equals plus or minus 2. So in this case, we get 2 more points. The x coordinate can be positive 2, and the y coordinate is 1. or the x coordinate could be -2, and the y coordinate could be, or has to be 1 in that case. These are all of the 3 critical points we've determined. We've got 0, 0, 2, 1, and -2, 1. And I left a reminder for us, which is important in single variable calculus extreme value theorem, and it's equally important in the multivariable calculus version, which is once we find our critical points, sometimes we can rule some of them out because they're not in the domain. So these are 3 different points in the xy plane. I'm just going to graph them. Here's 0, 0, and that's in the domain, so that one's good. 2, 1 actually is an issue. 2, 1's over here, so let's take that off the list because it falls outside of the domain. And on the other hand, -2, 1 is over here, so that one's good. So we actually only have a list of 2 possible critical points. And at this point, we could classify these as local max or min using the second derivative test. I think I'm actually going to leave that as an exercise for you. It's good to just work through that second derivative test theorem on your own, computing the discriminant for each of these points. If it's positive, it has to be max or min, and you can use the second derivative in the x or the y direction to determine what the concavity is. And if the discriminant is negative, then it's neither a max nor a min, and actually we can rule it out for the rest of the problem after that. But I'm not going to do that. I'm going to proceed by answering question C, which is, it's not necessarily true that one of these 2 critical points has to be the global maximum of the function. They might both be saddle points, and then we'd have to go look at the boundary. They could just be local max, and then the boundary could still have larger heights. But in any case, the maximum could occur somewhere other than the critical points, just like maxima in single variable calculus can happen at endpoints, even if we have critical points within the interval. So we need to pass to part D of the question, which is finding the maximum value of f, given the information we've assembled. So we know that it can occur somewhere on the boundary or at one of the 2 critical points on the interior. And in fact, one of the critical points is on the boundary. 0, 0 lies on the vertical segment that forms part of the boundary. So that should come out in the wash, what happens at that point. Let's find the maximum value of f. The first thing we're going to do is check what happens on the entire line x equals 0, which again is this part of the boundary in our semicircle picture. So on the line x equals 0, algebraically, we can plug in x equals 0 into the function and look at what the values of the function are depending on the height of the y coordinate in the xy plane. So if I plug in x equals 0, I'm just stuck with 2y squared. This is now a function that only depends on y because the x coordinate's fixed. And the maximum value of the function on just this part of the boundary, keep in mind, this is a radius 4 circle. So this is height 4, and this is height -4. And that means that the largest that f equals 2y squared can get is at either of those points. So that's going to be f of 0, plus or minus 4. And the height in that case is given by 2 times 4 squared. That's going to be 32. So at 0, plus or minus 4, the height of the function is 32. That seems like a pretty big height. So maybe that's the max value at either of those points. It's certainly bigger than one of our critical points, 0, 0, since we can plug 0, 0 into the function, or we can even plug, knowing that the x coordinate is 0, we can plug the y coordinate into this simpler function and see that the height is 0. So that's going to be either a saddle point, but probably a local minimum of the function, and maybe even the global minimum on this domain, which I'll leave to you to figure out yourself. Now let's look at the values on the semicircle. That's the rest of this domain, the boundary of the domain. And these are all of the points that satisfy the equality x squared plus y squared equals 16 and have x coordinate less than 0. So we've already dealt with the x equals 0 part on the vertical line. Let's deal with the semicircle next. And checking things on a curve versus a line tend to be harder, but in this example, and in many examples we'll see together, you'll notice that there's a hidden thing here, which is x squared plus y squared. There's 2 y squareds, but one of them I can pair off with x squared and just reduce this to the following expression. So 2 terms combined to give me 16, since the point lies on the boundary. I have an extra y squared hanging out, and I also have an x squared y. And actually, I want to get things in terms of a single function of y, again, just like we had previously. Let's replace x squared with 16 minus y squared. And I'm going to distribute and get all my powers lined up. It looks like I have y cubed, if I distribute the minus sign there, a positive y squared. Let's see, negative 16y and a positive 16. So this is a function of a single variable, and what this is really saying is that on our boundary region, just the semicircle, the height of the function in the z direction as we travel along this circle is completely determined by the y coordinate that we plug in. So the point at this height has a height that's completely determined by just its y coordinate, so on and so forth. That's what this is telling us. What's the maximum value of f on this part of the boundary? Well, we have a single variable function in terms of y, and we want to determine its maximum value on some restricted domain. This is the y values will actually be bounded by plus and minus 4. So we can think of this as a single variable EVT problem, and we want to maximize this function. Let's look at the first derivative of the function to find critical points. And the critical point, the first derivative is going to be 3y squared plus 2y minus 16. It turns out we can factor this as 3y times something, or plus or minus something, times y plus or minus something. So we need the 3y and the y to give us 3y squared. We need two numbers that multiply to give us negative 16. Let's start by thinking about 2 and 8. If I put a 2 here and an 8 here, I want them to add up to 2. And let's see, if I do 3 times 8 is 24, and I can't add or subtract 2 to get plus 2. So if I instead put the 8 here and the 2 here to multiply to give me 16, then I see I have a 6 on the outside when I FOIL, an 8 on the inside, and 8 minus 6 gives me positive 2. So I'll put a plus and a minus here, and this is a correct factorization. If you didn't know how to factor this, you could use the quadratic formula as well. In any case, this tells us that we set this equal to 0 to find possible maximum and minimum values. The y coordinate is negative 8/3 or positive 2 on the boundary, which means, and we can go determine the x coordinate using the circle equation. These points are possible points where on the boundary we have a maximum value of the function. They could also be minima. They could be fake out critical points that aren't max or min. And at this point, if you wanted to know along the boundary if these are critical points, if these two critical points just on the boundary give you max or min values, you could go test that separately. You could even use the concavity test for this single variable function to determine if you move along the boundary in either direction, are the slopes going up or down? Or sorry, is the concavity positive or negative? But you know what? We have a whole list of points to test, so why don't we just slide these in with everything? And if you work out the x coordinate, which you can see, you'll be able to see this in the textbook, worked out explicitly for y coordinate negative 8/3. This is just solving x squared plus y squared equals 16 for x and plugging in that y value. You'll get this number, 1264 over 27 as a fraction, which is about 46.81 as an output value, as a decimal. On the other hand, the x coordinate for positive 2 is going to give us an x comma 2, where x is whatever solves this equation. When y equals 2 is plugged in, that pair outputs negative 4. So at this point, we can rule out that point of height of x of y coordinate 2 from our list. And actually, this also eliminates another possibility because our boundary points of the vertical line segment, along the y-axis, gave us a height of 32 only. Those can't possibly beat this current answer. The only other thing that could happen to give us a larger f of xy value is for one of the critical points on the interior of the circle to give us a larger f value. So let's go check our list again. We got it down to 2 critical points, 0, 0, and -2, 1. So those are the 2 that we're going to plug in. And actually, we already know what the value at 0, 0 is, because that was on part of the boundary. So that just gave us a height of 0, and that's not going to be a maximum value. On the other hand, -2, 1, if we plug into our function, oh, let's see, I need to go look at what it was again. It's x squared plus 2y squared minus x squared y. That was our f. We plug in -2, 1, we're going to get 4 plus 2 minus 4, which is 2, which is nowhere near any of those other heights that we saw, or any of the other positive heights. So the maximum value of this function is 1264 over 27, which you said was about 46.81 as a decimal, and it occurs at the point blank, comma, -8/3 on the circle on part of the boundary defined by x squared plus y squared equals 16. So that's a full classification of the critical points and boundary points in terms of whether or not they can be maximum values. You can repeat this process, compute all of the values, and find minimum points to compare. And I believe in that case, this other point gives you the minimum value of -4. And I think we actually have already assembled all the information to tell that that -4 would be the minimum value, but you can go check that on your own. Great. That's a little bit involved of a problem. And that's kind of how it has to be in multivariable calculus, because we have domains that are 2-dimensional now. So we have infinitely many points on the boundary to check. The only way to do it is by start playing their equations off of each other to narrow our search down to a finite number of points. Here are some of the main takeaways that I want you to understand from this lecture. If the extreme value theorem applies to a given situation, then all we need to do is find the critical points and evaluate the function at each of them, and also evaluate the function along the boundary. And we're guaranteed to find the maximum and the minimum at one of those points. The way this first bullet point is written is a little misleading. It should say the critical points and the critical points of the boundary functions, just like we did in the previous example together. But these are all of the finitely many points where f could have a max and a min, and the extreme value theorem, when it applies, guarantees that the max and the min both occur somewhere. The gradient function set equal to 0 will detect critical points on the interior of our region, but not necessarily on the boundary. However, we can rewrite the function f on the boundary using some sort of substitution. For example, we used the substitution x equals 0 to find the critical points on the vertical line strip along the y-axis. We also used the substitution of x squared plus y squared set equal to 16 to reduce the complexity of the function along that semicircle boundary. Often setting the derivative equal to 0 of that simpler function, which is usually going to just be a single variable function, will help you to find critical points along that boundary component. And if you assemble all of these points together, you can detect the possible max and min values of the function. One warning is that the derivatives, be they partial derivatives or single variable derivatives, will not detect maxima at the endpoints of a boundary curve. For example, the endpoints of our boundary curve that was the semicircle, if we had done that first, had to be included even though they weren't critical points of the boundary function. These have to be included in your set of critical points, and this essentially only happens when you have sharp corners like we had the vertical line turning into the semicircle. That's all we're going to talk about. I know that wasn't a lot of practice problems, and it was one of our longer videos, but we'll have lots of practice problems together in class. And you can also write down any multivariable function that you've seen so far and try your hand at classifying its critical points as maxima, minima, saddle points, or otherwise. So here's some summary questions for you to think about. Where must the local max and min values of a function occur? And why does this make sense? Next, what does the second derivative, or what do the second derivatives, the second partial derivatives tell us about finding max and min of a function? What hypotheses do the extreme value theorem require? And what do these hypotheses tell us? And finally, assuming a maximum and minimum of a function exist, where must you look in a domain to be sure that you find them? I'll leave you with one practice problem shown here. We have a differentiable function f of x comma y on this domain. And the problem asks you 3 questions about this setup, including sketching the domain to check if the conditions of the extreme value theorem apply, and then asking about the conclusion of the EVT and the process you would take to go investigate the location of max and min if they exist. That's it. Thanks for tuning in. I hope you feel energized to go maximize and minimize some multivariable functions, and we'll do that in class together. So I'll see you soon.